I'm pleased to introduce for today's session, introducing Milvus Lite. Our guest speaker is Yang Chen, which is the head of AI platform and ecosystem at Zilliz. With years of experience in data infrastructures and information retrieval, Yang previously served as a tech lead and product manager for search indexing at Google. He holds a master's degree in computer science from the University of Michigan, Ann Arbor. Welcome, Yang, and the stage is yours.
Hello, welcome everybody. Um, let me do a quick introduction of myself. As Stefan introduced, I'm currently head the ecosystem and AI platforms. So I think in the past few months, I have been, other than doing the ecosystem integrations, I've been also leading this Milvus Lite project. And today I'm very excited to introduce this, new offering of Milvus to you, which is a lightweight vector database that you can run as a Python library in your AI application. It's super easy to install, super easy to get started with, and I hope you will like it. So without further ado, let's kind of review a bit of background, why we want to build vector database, and specifically easy to use, easy to install vector database that's perfect for AI developers to get started with their AI development stack. So this story of vector retrieval kind of come from the advancement in deep learning and neural networks. So traditionally, there was search by probability. There was search by terms and tokens, which is what the inverted index and stacks like Elasticsearch was used for. The idea is pretty much we break the documents apart into tokens and keywords, and then we also find the keywords. We also kind of generate the keywords from the query, and then we match the keywords from the query to the document, and then we finish the search. But this is so mechanic. The mechanical way of doing search results in some undesirable behavior, which is like, even though the documents is pretty much talking about the same idea as the query, it cannot be retrieved because the keywords doesn't exactly match. For example, what's your age is very, very different than how old are you. They don't share many common keywords, but they actually share the same semantic and same meaning. So this is how deep learning and neural networks come into play, which is using the idea of probability in search. So this idea is that with the deep neural network, we can kind of encode and represent the documents as vectors, and that kind of grasp the essence of the meaning of the document. And the same thing is done with queries, so that when you match the two representations of query and document, if they share this like a close if they are close in the latent space, like in another word, they have shorter distance between the vectors compared to the other documents and the same query, then there's a high likelihood that they share the same semantic meaning. So with this idea, there was many techniques and machine learning models and also data infrastructures built around this. Some of you may have known like embedding models in the architecture of, say, BERT, or even transformer architecture. And the vector database is a piece of infrastructure introduced for this, so that with the great models, now we can generate embedding vectors, and we still need something to store and efficiently retrieve the vectors. And that's what vector database does. And with this great technology, there's another kind of technical paradigm happened in the last 12 months and has been very popular among the AI applications and developers, which is called retrieval augmented generation. The idea is to use the embedding model and vector retrieval together with the large language model to improve the large language model's capability on some specific domain of knowledges. For example, if you are a company with internal data which you would not like to share with the external community or the wouldn't want it to be trained for the large language model I used as train data for large language model. In that case, you can still use this data to do, to build chatbots to provide great question answering experience to users with vector retrieval. The way it works is that it first index the knowledge base as vectors and store them in vector database, as was shown in the bottom left. So with these vectors, pretty much we have compiled a knowledge base that can be efficiently searched and retrieved from. And then when user asks about some specific question, in this case, the user may want to ask about a very specific index type question for Milvus, which the large language model probably don't know because it was not trained for the documentation of Milvus specifically. In that case, this query will be converted into a query vector with the same embedding model that we used for the documents. And the query will be searched in the vector database through approximate nearest neighbor search to find the nearest vectors, which very likely will have the similar meaning or related semantic with the query. And in that case, it's very likely those documents will answer the question. So once we retrieve the top K documents from the vector database, we can compose the prompt with user question and retrieve doc and some instructions and send it to large language model. So the large language model will be smart enough. It will be do some reasoning. It will do summarization, and then eventually provide a high quality answer that that matches the user's expectation. In this example, it will answer as of last month, it was supports 11 index types instead of just making something up. So with this background, why do we build Milvus Lite? Because Milvus is doing great in this domain. The reason is being, despite Milvus is loved by many developers, we kind of notice it's not that easy to get started with. So for example, right now, the easiest way to use Milvus is through a Docker deployment. And to use the Docker, you need to download some scripts, you need to run the script, even though not many commands, but it's still kind of scary to some developers familiar with, say, Python and pip way of developing applications. And also, it requires you to install Docker on your host machine or development machine. Right? What if we have something way easier? Right? Say, if I don't care about scalability at this moment, can I just use something simpler? Well, the answer is yes, because Milvus Lite is designed for this. So the idea is that instead of downloading Docker and a bunch of scripts, you just need to have a Python environment and do pip install PyMilvus, and that will do everything for you. It's pretty much just a Python library, which you can import, like the one we showed below. From PyMilvus, import Milvus client, and then you instantiate the client with a local file, just like how you use SQLite. So with this local file, it not only loads the data that you will insert after this into memory, but also materialize and persist them on disk as a file that's specified here. In this case, it's called milvusdemo.db. And in this way, it provides similar experience as the Milvus deployed on Docker and even Kubernetes. And this is very lightweight and efficient so that it can be run on your laptop, on Jupyter notebooks, and also on edge devices like smart home devices and mobile. So the way it works is we kind of strip off all the heavy lifting components of Milvus that's designed for scalability on distributed systems. Right? In Milvus, if you look at the architecture before, And there are query nodes, there are data nodes, there's Kafka for message queue. There are a lot of great things for handling the high throughput, high traffic, and designed for horizontal scalability, so that just by throwing in more machines, it will be more scalable. It can sustain you towards tens of billions of vectors as thousands of QPS of search and ingestion. However, that's not necessary for most of the AI applications, which is in its very early stage, right? Simply, I don't have many data. I don't even have, say, 1 million vectors, or I don't want to think about scalability at this moment. At this moment, my first priority is to move fast, or I just want to learn about the AI technical stack. I just want to learn about how to build RAG rather than having to install, say, Docker or Kubernetes as a prerequisite. That's too much ask. So this to solve that problem, we can strip off all the heavy lifting components from this so that it can be lean and small enough to fit in your local, say, laptop, or even machines with very limited computing resource, like edge devices. So what we keep here is just a very basic, very minimum of vector indexing and retrieval, and also persistent storage. So let's walk it through from the left to the right. Right, on the left, I have my user application, which is, say, AI chatbot. And in the chatbot, I imported Milvus client so that I have a client to talk to the I'm sorry. So I have the client to talk to the core of Milvus, which in this case is a server and a code. So the client can insert, upsert, and delete data records through Milvus Lite. And it first talks to a parser so that it can parse the query. The reason that we need a parser is not only the client will express the semantic of, say, inserting this vector for me. For the query, it sometimes for metadata filtering feature, it will also specify find the closest, say, top 10 vectors to this vector, but also following the filter expression, such as I want the subject to be history, I want the version to be 2.4.0 rather than 2.3.0, things like that. Right? So there's a expression that comes with it. So the parser is mostly used for parsing that expression and then convert them into an internal representation of this query intention, which we call execution plan. And the execution plan will be passed to the core for further processing. On the other hand, we also want to materialize the data insertion and deletion so that next time when you restart the program, all your state won't be lost. It will be reloaded from the local persistent file that we specified in the Milvus client instantiation. So there's a storage kind of converter which converts the insertion and deletion operations into file operations, and then materialize those data in the local file. So once doing that, now it's ready for us to do the real vector search or update or index to reflect the recent insert and deletion. So the core will actually talk to the in-memory index that we that's the state we keep in memory, and update the index so that the vectors are added or removed. And if that's a search, it will use the index to do any search kind of algorithm you specify, like HNSW or IVF. Depends on whether you care about that. If you don't care about that, you can specify nothing so that you use auto index, it will choose it for you. If you do care about the algorithm, then you can also specify which indexing algorithm it uses. So once everything is done, it will pass it back to parser and eventually back to the Milvus client. Now your user application gets the vector or it finished the operation on the vector storage. So with this design, now you can use Milvus pretty much everywhere. On your GenAI application, you just write the Milvus related client code once, like you instantiate the client, you do insertion, search, and this code can work with any kind of Milvus deployment, whether it's Milvus Lite running on computation resource or limited computation resource devices, or it can run on Docker, Kubernetes, and even cloud, like Zilliz Cloud, which shares the same API as Milvus. The only change that you will need is you still need to switch the endpoint in the Milvus client, because pretty much you have set up a new server, you want to express the server endpoint while establishing the client. But that's mostly it. And for the data, we also think about how to move the data conveniently from one deployment to the other deployment. So now Milvus supports this data import feature, which you can specify a file in either JSON or Parquet, and then you can load the data into a new collection on any Milvus deployment automatically with just an API call. And we are also in the process of developing convenient command line tools to help you do this, so that you don't even need to write a few lines of code to do the API call. In addition to the deployment, the flexibility on the deployment, we also integrated Milvus into pretty much any popular AI development toolkit, like some known things like Llama Index, LangChain, and other than that, we also integrate with a lot of embedding model providers like the Voyage AI and Gina AI, and OpenAI. They provide embedding model as a service. We also integrated with Bento ML, which does the model inference hosting. They have the open source and cloud offering, and we also implement with other like projects with very novel concepts. For example, Ragas, what they do is they integrate they kind of streamline the process of RAG quality evaluation, so that after you develop a vanilla RAG, usually you care about its quality and you want to do some experiment and measuring of the quality. Right? So with Ragas, what you can do is you can get the quantitative numbers out of your RAG implementation, so that next time when you change some implementation or you do some optimizations, it will give you a different number so that you can tell if this made it better or worse or how much better. And we also integrated with MapGPT, which is working on agent with memory. So vector database and embedding models, that's a great way to encode and store the memory of the agents so that they remember what the users has told them in the past. The Milvus, there is Milvus class integrating into MapGPT, so that in this agent implemented by MapGPT, you can use Milvus to store all the state, and you can share the benefit of the flexible deployment modes of Milvus. And we also have the data source friends like Airbyte, which can help you build the data processing pipelines, so that it can help you move the data from one source to another source and do the embedding and other conversions for you, and many more other projects. So I will pause here for some questions, and then after this, I will show you the documentation and some live code examples of Milvus Lite. Any questions from the audience?
There's no question directly so far. Someone was
Okay.
just very impressed by and happy about Milvus Lite in general, how easy it is to use.
Okay, then I think we can move on to the next chapter. So for the detailed information about Milvus Lite and also Milvus, you can go to Milvus.io website. And we have just redesigned the website to reflect a lot more information, right? So as I said before, now the Milvus Lite experience is just a pip install away. So once you pip install, you can use the same API shared between Milvus on Docker and Kubernetes and Milvus Lite for collection creation, and insert data, search, and others, which are quite intuitive. And so we also put the pointers of instructions on how to do different types of deployment. For Milvus Lite, that's kind of straightforward, just pip install. But for Docker and Kubernetes, it's a bit more complex. But you can visit the details for, you can visit the documentation website for more details. You can also find the helpful scripts from this install Milvus section, where it has Milvus Lite and Milvus Docker. There are different modes of Docker available, and also Kubernetes, which is a bit more complex. You need to set up the operators or use Helm to do the deployment. And we also linked the integration documents with a bunch of our partners. This is not a complete list. There are many more from the documentation. And lastly, but not least, we also have the in-person meetup called Unstructured Data Meetup, which happens in many cities around the world, from San Francisco, South Bay, to Berlin, and Seattle, and maybe New York in the upcoming months. So welcome to reserve a seat in the upcoming meetups, and talk with us in person. So without further ado, let's also check out the documentation, which has a lot of great coding examples to show you how to use Milvus Lite in action. So I will start with a quick start here. So this documentation, they are also designed as a notebook so that you can run it for you. In addition to copy paste the commands and run in your local development environment. And other than the basic stuff, we also have deep dive on different concepts in Milvus, such as, say, consistency, multi-tenancy, which are concepts mostly used for the Milvus server, and also how to use different kind of index to speed up your search performance, and detailed explanation of the schema and data model design, which we won't cover here because it's another big topic. But if you really want to design a very efficient system and can do very complex operations, learning about the schema design, that's very important. And in addition to that, we have very comprehensive integration documents. So as you can see here, we integrated with many partners in this list. And I will show, so LangChain, for example. For anyone working on retrieval augmented generation, probably LangChain and Llama Index are well-known and mostly used frameworks to help you design the data pipelines for indexing and data processing and also retrieval. And some even provide the agentic or agent capability. If we have time, I think we'll have some time. I will do a more deep dive on how to use LangChain to do to implement the advanced concepts in RAG so that I can improve the quality of the question answer. But the basic stuff is here. Okay, let's jump back to the get started. And let's run this in action. So as we mentioned before, the first step is to do pip install. And in this command, it will install both not only the client of PyMilvus, but also the server part of Milvus and the server part of Milvus Lite. I put the server under code is because, as we mentioned before, it's lightweight. So under the hood, what it actually does is it use gRPC to communicate between the client and the server, but not through a network, but through a local file. The local file is different than the local file for persisting the data. As some temporary local file, which is pretty much just used as a billboard to exchange information between Milvus and between the Milvus client and Milvus Lite server component. For convenience, we include all of the components in PyMilvus so that you can use PyMilvus. If you have a Milvus server, then pretty much what you want PyMilvus for is just as a client. But if you also want to use Milvus Lite with the PyMilvus, you also get the server part. In that sense, you don't need to install another Python package just to have an easier way of using Milvus. So with just pip install, you can import the Milvus client, which is the abstraction that we use to talk with Milvus. And in Milvus client, you can instantiate it with a few different ways. In this case, because we want to use Milvus Lite, we just specify a file name, and the client will be instantiated with Milvus Lite and will create this file for you. If you wanted to talk with some Milvus server that you deployed before, you need to specify the Milvus server endpoint and token, right? So if that's a, say, Milvus server on Docker, then it's very likely a localhost with the port, and then token depends on whether you have set password or not. It will be the username and password. If you are using, say, Zscaler Cloud, then it will be a network endpoint of your Zscaler Cloud cluster, vector database cluster. And then following that will be API key as the token. So still sharing the same function, sharing the same API, but with slightly different flavors. Let me run this for now. Yeah, so with this, we have created a new database. And right now in this database, we don't have any collection. So we need to create a new collection and specify the minimum that you need to specify is dimension, which is how many dimensions this vector have. But other than this, you can specify many more parameters, including if you want to design the schema yourself, then you need to create a schema object and then specify it here. For example, if I want to specify what kind of labels I have together with this vector and to specify that in the schema. However, if you don't have an idea what kind of labels you have at this moment, or you just want to omit them and just use anything and don't care about the performance implication, because by defining schema, you can define index on specific Scala fields like non-vector fields. In that case, it will do more efficient metadata filtering. But if you don't have many data, say if you just have thousands or tens of thousands of vectors, that's a very small scale of data. Then you don't have to specify that, and that's what we are doing here. So what this creates is a vector database schema with only ID, vector, and any kind of labels you want to put there. We'll see that in action in a bit. But before doing that, remember that to do vector search, we need to have vector in the first place, so that we need to install a package for embedding models so that we can convert, say, text into vectors. And we have provided a convenient wrapper called PyMilvus model. This sub package will this sub package it wraps a lot of model providers like what we mentioned before, OpenAI, Voyage AI, GenAI, and also open source embedding models like BGE and sentence transformers, which is good for many open source embedding models. So with it, we can convert the text. In this case, I put 3 example text strings as documents. We can convert them into vector embeddings with just a function call. So what we do here is we import the model package from Milvus, and we instantiate a new embedding function. In this case, because we don't really care about which embedding model to use at this moment, but once you are familiar with this, you probably have your own say on what embedding models to use because they have different quality implications, and sometimes the providers also develop the so-called vertical embedding models. Some are good for, say, legal content. Some are good for medical content or finance, things about finance. You can feel free to choose anyone that suits you, or like models suitable for different languages. But for the demonstration purpose, let's just use a small model called Albert Small V2, which has just 50 megabytes, so that within a few seconds it has been downloaded, so that we can use it to convert the embeddings. Now we have 3 document pieces, all talking about either AI or Alan Turing, who was kind of the founder of the concept of artificial intelligence. And we use embedding function dot encode documents with a list of documents to generate the vectors. Now we also have a list of vectors, and each one kind of mapping to each document element of this list. And the reason that we see encode documents rather than just encode is because due to the design of the embedding model, some use different methods or slightly different, adding slightly different, say, sort to the encoding process so that they encode the document and query slightly differently. So we hide this by providing 2 convenient functions, one called encode documents and another one called encode vectors, encode queries, so that you don't need to think about this and remember it, just to make sure that you use encode documents for documents and encode queries for the query strings. And for some of them, there's no such difference, then we provide just encode function plainly. And if you print the dimension of the both the embedding model and the vectors generated by the embedding model, they shall match the dimension that you specified above, which is, I think it's 768 dimensions. So here we can see after downloading the embedding model, it prints out the dimension matches what we specify for the schema of the collection. Otherwise, it won't work because you want this, what you insert to match what you define in the schema. And we also print the whole. We also construct the whole data object, which will insert into the vector database in one single operation. And in addition to the vector that we just generated, we'll also have an ID, which is used as the primary key, and also the text, so that when we retrieve the vector, we can also kind of carry out the text, so that we don't need to find the text in another place. Like we don't need to set up another SQL storage just for this. And also just for fun, I also added a label which is called subject that describes what kind of subject this is talking about. So for example, if I want to do a query, but only among the subject of history instead of, say, biology or something, I can specify the filtering in the query language of Milvus, which we'll show a bit later. Now we have the data objects, which has 3 entities mapping to the 3 string objects. Each has 4 fields from ID, vector, text to subject. If you couldn't, download the model for some reason, like network issue, in your local environment, you can also kind of generate the fake vectors just to finish the demo, but that's not interesting and we won't cover about that part. Now we have the real vectors, which represents the semantic of the text. And each one of them has a very interesting label called subject. We're ready to insert them into the vector database. So you don't need to set up any server at this moment because you already have the Milvus Lite covered you. And with this intuitive API client.insert, just specify the collection name, which we created a bit before, and the data object. And now it inserted 3 elements with ID from 0, 1 to 2. Now we are ready to do semantic search. Let's just make up a query, like who is Alan Turing? And as I said before, we need to encode it into query vectors. So this encode queries for convenience, it accepts a list of queries so that you can do multiple queries at the same time. But for this case, let's just do 1 query so that we have a list of a single query, and we generate a query vector of size 1. And we're ready to do search. Let's see how this search query is composed. So first, we need to specify the collection name. Again, the same collection we created and inserted data to. And the data accepts a query vector. The data field accepts a query vector list, which has just 1 single vector. And we need to specify limit. This is interesting. The limit is equivalent to the k in top k, meaning among all of the vectors stored in this collection, in this case, we have 3 vectors. How many closest vectors I want to get out of it? In this case, let's specify 2, because we don't want all of the vectors. Then it won't be interesting. And other than that, you also can specify the output fields. Like if you don't just want the vectors, you also want say the raw data where the vector was converted from, or some labels, you can specify them in the output field so that they will be carried out together with the vector in the result. Now let's run this. So you can see the result contains a lot of interesting information. First, it contains a data object, which is a list of results. For each result, it specifies the ID and distance. Distance is like the similarity score of the target vector. In this case, the vector for this sentence talking about where Turing was born. And the query vector, which is who is Alan Turing. And depends on which index algorithm and distance metric you used. In this case, we didn't really specify that, so we used the default. But if you have a say, you can define, for example, my index algorithm being HNSW, and my vector distance is defined by, say, cosine similarity, or IP, like inner product similarity. So it depends on which one you defined. The distance will be calculated in different ways. In this case, the distance actually describes how similar the 2 vectors are. But in other like distance metrics, the distance could literally mean how distant the two vectors are. So that will affect whether they are sorted ascendingly or descending. But either way, the ranking of the results is that they are ranked by the semantic similarity between them. In this case, the most semantically close one is where Turing was born, and then the second one is Alan Turing kind of invented the concept of AI. And because we specified the output fields to be text and subject, so that in addition to the vector itself, it also outputs the text and subject in the result. Okay. Let me see if there's any questions from the audience.
Yes, there's one, which is about parameterizing the query. I don't know if you've seen it. Do you
In
see
the
it?
chat,
Yeah, it's in
or
the chat directly from Alice. I can read it if you want. It's
could
asking
you?
if you can parameterize the query vectors, and also if it's possible to iterate over each record, like, similar to SQL Server, MySQL, to get the answers.
Iterate each record in a SQL Server, MySQL, other database to get the answer.
And it's a follow-up from the question that is above.
I see. So the result is actually just a list of entities stored in the database. So if you want to iterate through the result, then you can just implement a for loop for this. But let's say, I wonder if the question is about, let's say if I want to search for many items, and then can I just kind of have a pagination so that I can do 100 first and then another 100? Is that the question?
They just added a comment. No, they want to iterate the query vectors, so search for a list of items or database of items,
I
and
see.
maybe put them into a JSON doc.
Okay, so you have two ways to do multiple queries. One way is that you specify a list of one single query and then do the search. Say if you want to do 10 queries at the same time, right? You can just do 10 searches, which is not that efficient. In addition, you can also specify the data to be a list of query vectors of size 10. And the 10 queries will be performed at the same time in one single API call or operation.
And there's another question as well, which is, why does the greater distance indicate a better match in this notebook?
That's a good question. That depends on the distance metric in this case. I think if I don't remember it wrong, the distance here is defined as cosine similarity. And for cosine similarity, the greater it is, the better it is. But for other things, yeah, maybe I'm making up here. But I think for IP, the shorter it is, the shorter the distance, the better it is. So that really depends on which distance metric that you use in this case.
Thank you. And we have a follow-up as well from the previous question. I don't know if you read it, but it's asking, so is there a 10-item limit? So, like, do we have to put things into a function or something to iterate if we have more than 10, basically? Like, do we have to iterate over multiples of 10s?
Yeah. So there's a limit. I think I'm not sure if that's 10. It's either 10 or 100. But there's a limit. And with the limit, if you have 1,000 queries, I'm not sure you can fit 1,000 queries into one single search request. So yes, you need to iterate through, say, 100 at a time. You need to cut them into 10 batches. Hopefully that answers the question.
Thank you. Those are the only questions so far. Seems like you did answer the question, yes.
Okay. Yeah,
So
thanks a lot
perfect.
for the question. Let's move on to the more interesting topic here.
Go, go,
So
go.
as I mentioned before, we could define different subjects for different documents, right? And then during the search, we may just want to get the results related to one single subject rather than everything. Okay, let's insert more documents of different subject. Here I made up 3 more documents, which are related to, in this case, biology, and also somewhat related to machine learning and AI. So for the ID, we want to increment it a bit because we don't want to have different content with the same duplicate ID, right? So after we encode the documents into vectors, let's compose the data object here. We increment the ID by 2 to skip what we have used in the past, like 0, 1, 2. We also specify the vector field, text field, and subject. We want to match the same the schema of the vectors that we have inserted before. And for this whole thing, technically we call this an entity, right? So data contains a list of entity, just for the terminology. Now we can insert the data again. Now, I think in this case, we have 6 items, 6 entities in the vector database now. And we can do a search by specifying a filter. The only different part is the filter. The same, we use the same collection, also encoded the queries. You can specify multiple queries here. I can show you this maybe in a bit. And again, we specify limit by 2 because we just want to find 2 2 documents closest to tell me AI related information in the subject of biology, and only return me text and subjects because I'm not interested in the other stuff. So let's run this and see what happens. Now we retrieved 2 different results. One is something about biology and AI. The other one is also about biology. So as you can see here, first of all of the things, they come with the subject biology rather than say history subject. And secondly, both of the top 2 content, they are related to AI. I intentionally put this one, like DDR1 is involved in cancers and fibrosis, which is not related to AI, and it wasn't show up in the semantic search result. If we remove this, I believe the result will be different, but let's see. Oh, I think I made a mistake here. It shouldn't insert the data again, at least not without the same ID. Otherwise, there will be duplicate data. But it's okay. Let's see the point. Now the result shows something related to history subject and also biology subject rather than a clean filtering was applied. Okay, I think that's all for the basic semantic search. Just very quickly, if you want to do some other operations, like you don't want to do search, you just want to get something from the database, like if just give me everything about history here. You can also use a different query called a different function called query, which can return the results that matches a specific filter without the consideration of vector similarity. You can also directly retrieve the entity by their IDs. And after all this, if you want to delete some data For example, I want to delete everything about biology. You can also use the delete function by specifying the collection and filter. And after terminate this thing, next time if you want to load the existing data into the into memory, you can just specify the client instantiation with the same file name. In this case, all of the existing data will be loaded. And you can also drop the collection if you don't want them. After you finish developing the stuff with Milvus Lite and you're happy with it, but maybe your user grow from say 10,000 to 500 million users. Glad for you. In that case, you can move to a more scalable version, which is Milvus deployed on Docker or Kubernetes. In this case, probably you need Kubernetes like a cluster, a gigantic cluster for vector search. In that case, you just need to substitute the URI with your network endpoint and token. If you have a self-deployed one, then specify your username and password. And boom, all the other code will work for the Milvus server. Okay, that's everything I want to show in this webinar. I think we probably have some more time for the questions.
Yes, thank you very much. People were quite impressed. Also really happy with filtering and different things that we have. Do people have some questions, maybe? People
Yeah,
are
thanks
happy
for
about
the
the webinar.
support. Maybe lastly, kind of a quickly go over the documentations we have. So we recently added many integration documents for our favorite, our lovely partners, including the known names like Longchain and Llama Index, so that in this one you can also use Milvus Lite. Like for Longchain, you just need to specify the the local file name in the Longchain vector store API, and then you have a vector store from Milvus Lite. And also you can use it with many embedding model providers from OpenAI and Voyage AI. And we show the examples how to combine them together and build your semantic search or RAG or image search. And also, very recently, I noticed there was a project called DSpy, which is very popular. We also have the integration with DSpy, where you can use the Milvus abstraction called Milvus RM in DSpy, which works for both Milvus Lite and the Milvus server on Docker and Kubernetes.
Ooh, thank you. Yes, I'm just answering questions directly from people. They're more about like the meetups. So I think we streamed the meetups in San Francisco, right? They're directly streamed. So yes, otherwise they're recorded and then it's always on YouTube.
Yes, so for the meetups, we do have recording and streaming for the meetup. If you want to check out the content of the past meetup, please visit our YouTube channel, and we have all the great recordings there. For the upcoming meetup, you can RSVP here, and we'll have the live streaming I think on Twilio. Yeah.
Yeah, and yes, the recording will be shared, and the code as well. I mean, the code is already available directly on the documentation. So if you want the code, you can just go there directly as well. But I think that's it. Thank you very much for the webinar, sorry, and for showing Milvus Lite. So yeah, for anyone, check out the website milvus.io. Also check out GitHub directly, and yeah, go for like the pip install PyMilvus. Go crazy on your machine. Break your laptop again.
Yes, please try it out and let us know how it works for you.
Yes.
And if you can, give us a star on GitHub, that will be a lovely addition to this. And also, we have announced the launch of Milvus Lite on Product Hunt. And today I think it's, let me refresh it. It's ranking as, yeah, 17th place. If you can give it a upvote there, which I included a link in your chat, that would be awesome. And thank you so much for your
Thank you
support.
very much. Thank you, everyone. Have a lovely morning, afternoon, evening, wherever you are. And see you for the next one. Bye.
Bye.